Adam is currently a PhD student at MIT. Uh, and I think before that, if I understand correctly, he was working at Foxconn with Minshew and others. And yeah, like he has worked on several interesting topics and in quantum information. And at the moment, like there is very nice paper that appeared recently on about quantum error correction. And and some of us thought that it would be awesome to listen to Adam because first, like I mean, the paper is awesome, and second, we have heard good things about Adam as a speaker. So from Minshew and others. So let's say like let's welcome Adam here, and Adam, like the stage is yours. Like yeah, please present.
Ruby, that's a that's a hugely complimentary introduction. Let me do my best to share my screen now. How's that looking?
Can see it.
That's good. Okay, okay. So yeah, thanks again for that awesome introduction, and thank you for having me. It's great to be able to talk to you. I should apologize if I'm a little bit slow or anything. It's on the later side in Boston. But anyway, this is going to be quantum codes with addressable and transversal non-Clifford gates. And first thing to say is that part of this talk is out. This appeared on the archive in February. And then there's another part of this talk which is unpublished. And I suppose the cool thing is this is actually the first time we're publicly announcing this at all. So you are the first people beyond the people listed on the screen that they're going to hear this. But this is joint work with friends at MIT, Sunny, Vinod, and Rachel. And so I'm going to be talking about some codes with some cool properties, new properties, but I'll start by motivating and defining what those properties are, and then give you an idea of what we achieve with these properties. And then I'll relate it to some previous work to say why these properties are new and what people have done before. And then I'll be able to dive into some of the methods and talk about how we get there. I'll be able to go into one of the constructions in quite a bit of depth, and then kind of gloss over one of the other ones before summarizing at the end, giving some open problems. And just before I start, I will say as well that I practiced this earlier and it did come in under the hour. So please do fire any questions at me that you might have. That's totally fine. So let's think about what we want out of our codes. The obvious thing to say is that we want to protect quantum information from noise. And I would like to do that with a reasonable overhead. And that is a very brief summary of the field of quantum error correction. It's also desirable not just to store this information, but also to be able to perform computation, quantum computation reliably in the presence of noise. And we're asking to do computation on the qubits encoded in the code. And this is a very brief summary of the field of fault-tolerant quantum computation. So what's our wish list for these codes? Well, the first two most obvious things to say just have to do with these very well-known code parameters. And this is that relates to the first point on quantum error correction. The first thing, we would like large dimension. The second thing, we would like large distance. So again, the dimension, that's your number of logical qubits. We would like to pack a lot of logical qubits into a reasonable number of physical qubits. And you can also capture this with the rate, which is just the dimension divided by the number of physical qubits. Just the ratio of logical qubits to physical qubits. We would like a large rate, otherwise known as a large dimension. And then your second part is just to do with how many errors can you correct? How much noise, in a very simplistic, quite a coarse way, how much noise can you withstand? So the distance can really be thought of as how many errors can my code correct? And so these are a quick summary of what we want for quantum error correction. But the third thing on our wish list is a bonus. And it's asking, it would be great if this code also came with some native way to perform quantum computation or just some quantum computation fault tolerantly on the code. That would be really cool. You don't have to have this third point. You can have just the first 2 points, and maybe your code would be great for storage, or I don't know, something else like communication. But having this third one is awesome for computation. And the classic example of a fault-tolerant operation is a transversal operation, and that's going to be central for us. And I'll start with a simple example, the example everyone gives, which is the Steam code. And the Steam code is a code on 7 physical qubits. It encodes 1 logical qubit, and it has a distance of 3. By the way, can you see my mouse? Just because I'm pointing at stuff, and I don't know if you can see my mouse. Great. So this is the 713 Steam code, and aside from having these error correction parameters, it has this nice property, which is that when you act on every physical qubit with the physical Hadamard gate, that has the effect of executing the logical Hadamard on the logical qubit. We say that this code supports a transversal Hadamard gate, and you can write this situation down very succinctly like this. H times 7 equals H with a bar. And as is normal throughout, we'll just write a bar on top of logical stuff. So the logical gates, the logical qubits, and so on. So this code supports a transversal Hadamard gate. And this is a like a standard, well-understood notion. I hit every physical qubit with the same gate, separately in a tensor product, and it has the effect of executing that same gate on the logical qubit. But there's loads of different ways to generalize this notion. And I find that the literature is a bit of a mess. Like there's, this thing is strongly transversal, weakly transversal, fold transversal, like all these different things. And it's hard to keep up. And especially when we're not just talking about single qubit gates here, if we're talking about multi-qubit gates, there's a ton of different ways you can do this. The most general thing you can say, most general notion of a transversal operation is that I'm acting on the physical qubits of the code with a low depth circuit. And that's having the effect of executing something interesting or something useful on the logical qubits. So of course, this is a depth 1 operation because it's acting with a single qubit gate separately on every physical qubit. In general, you would just ask, let me just do a low depth operation, and the logical operation should be interesting or useful. So let's talk a bit more about transversal operations. The point of them is that they're inherently fault tolerant. The reason they're inherently fault tolerant is because if you have this physical circuit being low depth, especially if it's constant depth, the errors cannot spread far. And so we hope to be able to catch them with normal error correction procedures, syndrome measurement, decoding, correction, that kind of thing. So we hope to keep the error rate down because the errors cannot spread too far. Transversal operations are super cheap to perform. Many other fault tolerance procedures, you might think about magic state distillation, you might think about code surgery, other things. You need to bring in ancillary qubits. So this is a certain space overhead that you're adding. And also the time overhead is really just negligible. This is a low depth, ideally a constant depth circuit. This time overhead is like nothing. And this can also be contrasted with certain other fault tolerance procedures which take a longer time. And the third piece of good news I'd say is that certain hardware, certain pieces of hardware are really, really suitable. And the one I'm really mainly thinking about is the Optima arrays. So that's the good news. What is the bad news? Well, the main piece of bad news is that you can't just do transversal operations. It is well understood that you will not be able to get a universal set of gates on a serious code to be transversal. This is the subject of the Easton-Nil theorem. It's a very well-known theorem. You need to do something else to get to universal fault-tolerant quantum computation. So you cannot expect to just be doing constant depth circuits on your code and be able to just do universality that way.
Can I ask a question?
Please.
Definitely, the Easton-Nil theorem and this generalization, like Brabby-Koenig and so on that we know. Any of them, do they assume if they, let's say, they don't assume any non-local operation, right? Let's say if I have something like these recent quantum LDPC codes, which allow for some non-local operation, check measurements. For this kind of codes, does Brabby Koenig, or let's say Easton Neal, still hold?
Yeah, it's a good question. And so the Easton-Nil theorem is just a statement about quantum codes. And so it has no assumption on locality. No assumption on locality. Now, the Brabby-Koenig result that you mentioned, I'm vaguely aware of this result, and I'm ashamed to say I don't know what it says. I think it's morally saying that 2D codes only have transversal Clifford operations. Is that right?
So Brabby Koenig, I think that gives you a hierarchy. Like it says that if you are in dimension, if the codes are d-dimensional, then basically you are able to implement transversally gate from dth level of Clifford hierarchy. But if I understand correctly, they in their proof or something, I don't remember exactly. Like they go through, some locality argument, and I was wondering, if let's say this non-local the quantum LTPC code with non-local check measurements, which where you allow for non-local interactions, whether by varying tuning the amount of non-locality there can be a way to go around Brabby-Koenig, maybe. I don't know.
Oh, I see. Yeah, I mean, there would definitely be a way to go around Brabby-Koenig. The really good quantum LTPC codes that we know are not geometrically local in 3D or any number of dimensions. And so you'd absolutely be able to get transversal operations really high up the Clifford hierarchy. But it's also worth emphasizing that you're never going to be able to get around Easton-Nil, because Easton-Nil is like assuming no locality at all. So it doesn't matter. You assume a ton of non-locality, you're able to get some transversal gate really high up the Clifford hierarchy. You're still just going to be restricted to that. So just to make things a bit more concrete, in this talk and with what we're talking about, you might construct a code with a transversal non-Clifford operation. You would then necessarily not be able to have that code also support all the Cliffords transversally, because of course all the Cliffords plus that non-Clifford, then you get universality. That's forbidden by Easton-Nil. So yes, you can build codes with a non-Clifford gate transversally, but you're not going to be able to get all the Cliffords. There would always be something missing. Does that answer the question?
Yeah. I'm definitely when we talk about Easton-Nil, that's about these depth one circuits, right? Brabby-Koenig goes a bit beyond that. So I think maybe Easton-Nil may still hold, but I was thinking, maybe the Brabby-Koenig, if you offer constant depth and not depth one, maybe there is still some room. I don't know. Yeah.
Sadly, I should, but sadly, I don't know the statement of Brabby-Koenig like in depth. I haven't read it in depth. I'm just kind of aware of what it morally says. So yeah.
But Kishore, I think the problem with geometrically local, if you want to generalize it, is that it only makes sense to talk about a d-dimensional lattice if you have the locality condition, right? Because what do you even mean by d-dimension if I allow arbitrary non-locality in a lattice?
Exactly.
I will say there is an notion there.
This is the reason. Yeah, lovely.
There is actually an interesting notion there, which would be if you're taking larger and larger products, even if it's not geometrically local. For example, you can have a code that's not geometrically local in 2D, but at some level it's kind of topologically two-dimensional. Like if it arises from just one hypergraph product. So there's this. I do know this result that says that if you just take.
You can maybe think
product,
of
you get Clifford if you take a hypergraph product, then you can only get Clifford operations, and so you need to take higher products. This inspires a lot of the recent work. You need to take higher products to get non-Clifford operations to be transversal. So that's an example of something that's kind of topologically, let's say, two-dimensional, but it's definitely not in geometrically local in 2 dimensions.
I see.
So basically, what dimension, Jinming, what I was thinking, maybe something like, so there have been recent results by Babsin and I don't know whether I pronouncing his name correctly, with other people, which they use this fraction right? Like based on graph, you can define dimension. So let's say you don't have, like geometric locality, but you have some connectivity graph. And then based on that, like you can define a dimension which need not be, like integer dimension, like this assault dimension, or like this, or basically those generalization. And maybe for these graph dimensions, which can be for the connectivity graph, which need not be integers, one can come up with, like analog of Braviconic or something, which will be better able to capture, like quantum LDPC codes, which has some amount of non-locality. Because geometric locality, as you very rightly pointed, right? I mean, there does not make sense. Yeah.
It's actually, it's a very reasonable point. I don't know that to be possible or impossible. That is an interesting question. So as far as I understand what you're saying is, could you quantify the amount of non-locality required for transversal gates going into the Clifford hierarchy?
Yeah. Another thing, like that we have been thinking of is, like let's say many of these things, like they always think of our subspace, but then there are, like these protocols which allow for, like going from one subspace to another, then another, like basically dynamical codes or flocate codes. And they are like, you can think of morally that has some relation to code switching, because the information you have to pass when you go from one subspace to another and then another and so on. And whether those code, like those dynamical codes can, like, so I was thinking, I haven't formalized it, but, I was thinking that maybe, like one can take some of these Baspin result and try to build a lattice, not in space, but in space time. And then there maybe try to show if some analog of, like Braviconic holds or not. So that will be generalization of Braviconic, and which was generalized for subsystem codes, but maybe one can think of generalization to like these dynamical codes and so on. But yeah, I mean, just wanted to, throw some stuff around.
That's actually a super interesting idea. Generalizing that sort of non-locality to space-time. That's super cool. It's easy to say words. With that, let's get back to the bad news. Eastern nil theorem prevents us from implementing a universal set of gates transversally. And so we need to do something else. And traditionally, we think of that something else as being quite expensive. And we think of anything that's non-transversal being quite expensive. That might be your magic state distillation. It might be your code switching. It might be your surgery or something. And because it might bring in more qubits, it might require high depth circuits, something else like that. We think of this as being quite expensive. The other kind of bad news, or at least roadblock, is that we find it really hard to make codes, just as a mathematical challenge. We find it really hard to make codes with transversal operations that are really interesting, particularly non-Clifford ones. It turns out to be really mathematically natural. We actually just touched on it briefly in that discussion when we mentioned hypergraph product codes. It turns out to be really mathematically natural to get codes with transversal Clifford gates, but getting codes with transversal non-Clifford gates is somehow quite mathematically unnatural and quite tricky. And so that's a bit of a roadblock in the way. But even with all of this good news and bad news said, it does make sense to try and get the most out of our transversal gate set. We can't expect to do universal quantum computation. It absolutely makes sense to ask ourselves, what kind of gate sets can we get transversally? How can we get the most out of our transversality? So we minimize the burden on anything non-transversal. And before I move on to our key notion of address, let me motivate this key notion of addressability now, because this key notion of addressability is going to be what's going to be maximizing our transversality. And to motivate that, let me just say a few words about low rate codes. If you consider a very low rate code with one logical qubit, like the surface code, then somehow transversal gates are quite easy to design. There's only one logical qubit to worry about. And so somehow it's easier to just talk to that logical qubit and just do a transversal operation to operate on that one logical qubit. And this is a very good reason, and perhaps even an underappreciated reason, that logic is so easy to do on the surface code, is that there's only one logical qubit to worry about. And so you just hit it. And we also saw this earlier in our Steam code example. There's just one logical qubit. But the fault tolerance overhead is massive, and obviously we want to get the fault tolerance overhead down. And one way to do that is to scale to higher rate codes, or equivalently add in more logical qubits to the same number of physical qubits to reduce this overhead. The problem immediately comes that when you have more logical qubits, it's very hard to talk to particular logical qubits. You might act transversely on the physical qubits to try and do something to the logical qubits, but it becomes really hard, and you might start acting on stuff accidentally, and it's very hard to just identify one logical qubit and talk to it. And this is what we mean by addressing. We want to address a given logical qubit and act on it with a transversal operation. And this is something that many papers just ignore. If you look at a lot of fault tolerance proposals on high rate codes, when talking about transversal operations, they will actually just act on every logical qubit at the same time, which is fine in certain scenarios. But it's really not what we ultimately want. We want finer control. I mean, ask yourself, how many algorithms are there where it's useful to hit every qubit with the same gate at the same time? And you may say, oh, well, there's the Hadamard. Hadamard, you get everything. And that's true. Beyond the Hadamard, it's hard to think of examples. Clearly, we want to be able to address particular logical qubits with gates. And so now I'll say what we really want, the real wish list. We want to be able to transversally address operations on a high rate code. So we want a high rate code, lots of logical qubits, and we want to be able to transversely address certain operations. So we're not just saying now there is one transversal operation, one low depth circuit that we can do on the physical qubits, and it gives us something interesting. What we're now saying is there are going to be many different low depth circuits that we can do to do lots of different desired things on the logical qubits. In particular, now we're saying, you want to talk to logical qubit number 12. I will give you a low depth circuit that you can do on the physical qubits, which will execute an operation on logical qubit number 12. So we can transversely address stuff. The physical action is a transversal low depth circuit. The logical action is to address a particular logical qubit. That's what I've just said. And we want to do this for the hardest gates, the non-Clifford gates. I mentioned earlier, getting codes with transversal non-Clifford gates is really hard. We're now asking for transversely addressable non-Clifford gates. Just for a bit of context, there were some works last year that constructed the first asymptotically good codes to have non-Clifford transversal gates. This in particular led to the discovery of constant overhead magic state distillation. But these also suffer from this problem of you're going to hit every logical qubit at the same time. You've got no amount of control of what you want. This is fine in magic state distillation, but clearly for more broad computation, we want to do better, okay? So this gives me enough. I think that's plenty of motivation now. We can state our results. So result one, our main result, is we construct the first quantum codes to support transversely addressable non-Clifford gates, and we get these things to be asymptotically good. And in our case, we end up looking at the CCZ gate just because it's kind of the most convenient thing. Oh, and let me also mention before moving on, this result one, our main result, this is the stuff that's unpublished at the moment. Everything else can be found in the current archive posting, which is linked here. Unpublished work, which will come out at some point, contains this result one. Let's clarify the exact meaning of the transversely addressable non-Clifford gate just to hammer it home. The CCZ gate is, of course, a 3-qubit gate. What I mean when I say we can transversely address it is if you pick any 3 logical qubits, perhaps any 3 logical qubits in the same code block, perhaps across 3 different code blocks, maybe there's 1 in a different code block and 2 in the same, then I can give you a depth 1 physical circuit which will execute the logical CCZ on those 3 logical qubits. So we have a very strong form of addressability. We have a high degree of logical control. So again, this unpublished result one, one of the problems we have with it, it's not clear if it's explicit or not entirely clear. We think it probably can be made explicit, but we're not 100% clear. And just as a reminder, the word explicit, it's essentially an algorithmic statement. It's saying that there is a polynomial time algorithm to construct this code. Without explicitness, you're just saying this thing exists. And you could, in theory, find it in exponential time. Thus, without that explicitness, we also have this result 2. This is an explicit code with a transversally addressable CCZ gate, and its parameters are only nearly asymptotically good. And this result 2 is found in the archive posting from back in February. And so here the parameters are only nearly asymptotically good in the sense that we lose a polylog in the rate and we lose a polylog in the distance.
I don't know, like even very like I don't know, maybe that's not a concern when we are doing asymptotic analysis and all. But I'm trying to think, like let's say tomorrow, like I want to go and implement and so on and like whatever. What are the weight of these codes? Like, I mean, like what is the weight of check measurements that you need to perform? Like, I mean, did you study? Did you guys like? I mean, is it like? I mean, definitely they are LDPC codes, so it's constant and all. But
well,
no,
like, these are not LDPC codes.
Oh wow.
So what we're studying is
we're
studying properties for codes that are new for any code. These are sufficiently hard properties to obtain that they are unknown for LDPC codes or anything. And these codes are not LDPC. They are, as I say, these properties are kind of hard enough to get for any code. It is actually reasonable, now that we've got these things to be asymptotically good, it is actually reasonable to say that there are certain LDPC constructions that we should be able to get this thing on, because like somehow all we're saying here is if your code has a really nice algebraic structure, which is already allowing transversality, then you can kind of, I'm spoiling a little bit, but it's okay. You can kind of use automorphisms to get the transversal addressability, assuming your code has those. And it is actually reasonable now that we've got these ideas to say that there are some LDPC constructions which should support these things. But yeah, as I say, no codes had these before, LDPC or otherwise. In terms of, you mentioned kind of implementation, I think there's two things to worry about with implementation. One is, I mean, at the absolute most basic level, there's the LDPC and there's the size of the code. Like these are just asymptotic parameters, but like what actually, is it going to be at finite lengths? And the nice thing about result 2 is because it's built from Reed-Solomon codes, the feeling is that it should perform very well finite lengths. Result 1 is obtained from algebraic.
Reed-Solomon codes are not LDPC, right? I mean,
right? Yeah. No. So again, these codes are not LDPC. But the feeling is that finite length performance will be very good for Reed-Solomon based codes. The algebraic geometry construction is awesome asymptotically, but is just a theory thing. The Reed-Solomon based construction, it could be quite good at finite lengths. I will say that
I don't know. I mean, there was a recent paper, right, which was like subsystem hypergraph product construction, where the code was, was not actually LDPC, but then they develop a subsystem version of that. And by measuring basically, like a small weight check measurement, they managed to, infer the stabilizers and so for concrete instances, maybe that can help. I mean.
Maybe. Yeah, no, so are you saying that somehow they can infer large weight stabilizer measurements by doing low weight
you can do this thing called like subsystem like you can develop subsystem codes, and for subsystem codes basically you can do these small weight check measurements, and so they form something called gauge group. I mean you can find it online, and then there is this I mean the stabilizer is basically something that commutes with all of those elements. So by measuring, like those non-commuting small weight check measurement, you can infer the syndromes corresponding to your stabilizer. And there is obviously there is a subspace that gets disturbed. So that's like gauge degree of freedom. So you don't worry about that. So I don't know, I mean, some subsystem construction instead of some subspace construction can help you get around this, like LDPC issue.
Not likely, because it really sounds like they're relying on the hypergraph structure there to get a gauge group. It's not likely here because we're using classical algebraic codes. As I say, now that we've got these ideas, so any code, there is a reasonable hope you could get this. That you can look at certain LDPC constructions with non-Clifford transversal gates and ask, can you get transversely addressable gates? I think it's likely, actually, now that you've got these ideas for just any code.
Yeah.
Cool. So results 1 and...
Hey, Adam, sorry, a stupid question, but like in the double brackets in result 2, what does the subscript 2 mean?
Just says that this is a qubit code.
Yeah.
Oh, I see. Got it. Understood.
Yeah. Thanks for the question. Okay. So results
sorry,
1 and
Adam,
2.
can I ask another question on this slide before you move on? So just to clarify, so when you say one or multiple code blocks, so you can have multiple copies of this code, and then you can perform like CCZ addressably across those copies. Is that what that means?
Exactly what that means. Yeah.
Okay.
Yeah.
Thanks.
Thank you for the clarification, actually. Exactly as you say. In the paper, we call them like intra-block versus inter-block. So intra-block meaning like, logical qubits within the same block, and I can hit those with CCZ, or I can say CCZ. So this is kind of the trade-off we're saying here. We now have a code with a really unbelievable amount of kind of logical freedom, but it's not LDPC. This is what's going on. Cool. So results 1 and 2, they have this ability to hit any 3 logical qubits. So they have this very high degree of transversal addressability. But one drawback is that we use very particular classical codes to get them. So as I'll speak about a little bit later, we use particular algebraic geometry codes to get this result 1, and then we use Reed-Solomon codes to get result 2. And we're not so satisfied with this because we're studying transversal addressability. We would like to understand this notion from a broader viewpoint. And so we develop a general framework for understanding transversely addressable gates in the diagonal Clifford hierarchy. And so we're able to reduce a bunch of these quantum properties to classical code properties to say, if you have this, then you can get that. And one of the products of this is our result 3. So you remember on the previous slide, we had a code that was asymptotically good, but we can't prove it's explicit. That's our result 1. Result 2 is explicit, but it's not quite asymptotically good. Result 3 is explicit and asymptotically good, but the transversely addressable CCZ gate is weaker. We can only address some triples of logical qubits. And to illustrate that, I've got this slightly janky diagram. Results 1 and 2, this is just an illustration. Imagine you've got code blocks here. The orange is like 6 logical qubits in one code block. The green, another code block. The blue is another code block. And this is just some random examples of things we can do, but you could pick any subset of this of size 3 and put a loop around it. But this is just to emphasize we can address stuff going across, stuff in the same one. Whereas the addressability of result 3 is weaker. Strictly what's happening is the logical qubits in a given code block are partitioned into sets of 3, and we can only address CCZ on each of those sets. So this is a weaker form of addressability.
But Adam, there is this notion of like swap, like I mean, like swaps often people consider like free in many platforms and all. So you can always swap qubits, right? And then it may not be a problem.
How much transversality would you lose if you did that?
Sorry?
Would you lose transversality when you did that?
Yeah.
So, yeah. But yes.
I mean, like, it's common, right? I mean, many platforms allow that. So, like, when you can have transversality plus some swap. Yeah.
Yeah. So, I mean, with a lot of these results, it would kind of be possible to go a bit beyond them if you sacrificed a bit of transversality, and then there's a question of kind of how much would you have to kind of want to sacrifice. But this is a fair point. Yeah, it's just that to get kind of the maximal addressing, being able to address any three requires your code to already come with a bunch of these automorphisms. So that I suppose actually one way, this is interesting, I suppose one way to look at it, if you like, is that result 1 and 2, like the code already has a bunch of automorphisms in some sense, so that the logical swap can be done, which is kind of adding that to result 3, and then you maintain the transversality when you do the logical swap. That might be one way to look at it, actually. Actually, I think that is a way to look at it. So anyway, let's plow on. I'm just going to mention these really quickly. These are just some of our small results. It's a bit of a long paper, but we try to talk about things with as much generality as possible. So we discuss things beyond qubits. You know, this stuff all generalizes to any qubits of your choice. And we also discuss gates beyond just CCZ. You can also think about CCCZ, CCCCZ, or even things more general than that, products of these things in particular. So you can get like highly specialized, transversally addressable non-Clifford gates. And then there's also a smattering of small results. We go on and we talk about parameters, stuff like this a bit. We also talk about T-gates briefly in an appendix. T-gates are kind of interesting. They behave very differently to CCZ gates in terms of both transversality and addressability. We developed this notion to get transversely addressable T-gates up to Clifford corrections, but we don't really have an instantiation in mind. So we're just reducing this to another classical coding problem. So I'll spend most of the rest of the talk talking about results 1 and 2, but I also just want to flash through some previous work because I just think a bit of context needs to be added. Because you might be wondering, how have people addressed logical qubits previously in high rate codes? It's not at all that it's not possible. It's just that generally it wouldn't be done with transversality. So typically addressing logical qubits was done with mostly peaceable fault tolerance and code surgery. And these are more expensive techniques than transversal operations. You either will have to incur some space overhead, bringing in more qubits, or some big time overhead. It's also definitely worth saying that the overhead of these, especially the surgery, has improved hugely recently in a really cool line of work. However, it doesn't matter how much you improve this stuff, it will always be more expensive than transversality. Transversality, 0 ancillary qubits, and a constant depth circuit. You want to be able to transversally address stuff in an ideal world. And so this stuff can improve as much as it wants, but at least in theory, it will always be more expensive than transversal operations. You might ask what's been done previously for transversal addressability, and it's been achieved for Clifford operations. Worth mentioning that these codes are LDPC, but they only get transversal addressability for the Clifford operations. So let's move on to the methods, and I'm only going to have time to talk about results 1 and 2. So again, that was our full addressability. We can address any 3 logical qubits with the CCZ gate. And we're going to rely on very particular classical codes to do that. And to start with, I'm going to reduce the problem, because it turns out that building codes with these sorts of properties directly on qubits is hard. There's no known way to get serious codes with serious parameters, and by that I mean like asymptotically good or near asymptotically good, with transversely addressable non-Clifford gates, or even transversal non-Clifford gates directly on qubits. And so in these works from last year, the works thought about a certain workaround where instead of thinking just about qubits, you think about larger qubits, and in particular, you think about qubits whose dimension is a power of 2, and that ultimately allows you to convert down to qubits. So let's talk a bit about these larger qubits and kind of how we think about them. So start off, fix q to be some power of 2, and think about the field of q elements, and we'll write that as fq. Quick reminder, given any prime power q, there is one field of order q up to isomorphism, and so in particular, if q is a power of 2, there is exactly one field of order q up to isomorphism. And so we can unambiguously write that as fq. What we then want to do is we want to write the computational basis states for this q-dimensional qubit via this field. So of course, if you're looking at a qubit, we write the computational basis states as 0 and 1. In some sense, that's labeled by the binary field, which is 0 and 1. But then when we go up to q-dimensional qubits, for our purposes, it is not convenient to write down these computational basis states as 0, 1, 2, 3, 4, 5 up to q minus 1. It's convenient to write it down in terms of the field elements. This is one way to build this type of a q-dimensional qubit. It's called a Galois qubit. There is another way called a modular qubit. But anyway, this is the Galois qubit. This is the one we want. And what kind of gates do we have for this thing? Well, this is the notion of a CCZ gate for a q-dimensional qubit. So, you know, we all know what the qubit CCZ gate is. This is the qubit CCZ gate. This is going to be a 3-qubit gate, just like the qubit version. And it acts on computational basis states in this way. So let me just go through this. One thing that's a bit odd about the qubit CCZ gate is that there's many of them. It's not like the qubit CCZ gate where there's just one. Here we have lots of different gates labeled by the elements of the field. So you take some beta in FQ, and then this CCZ beta gate acts on the 3 computational basis states in this way. So you multiply beta with all of these computational basis elements, and then you take this linear map, which gets you down from the big field into the binary field. This is called the trace map. And that gets you a 0 or 1, and then this will tell, this will decide whether you're going to put a phase of +1 or -1 here. Okay, and we can compare this to the qubit CCZ gate. There's the clear analogy. CCZ acts on x1, x2, x3 by taking the product of these 3 and then taking -1 to that product, such that we add a phase -1 if and only if x1 equals x2 equals x3 equals. You might wonder, why are there many different CCZ gates for the qubits and there's only one for the qubit? Well, you know, in theory, there are many, or there are 2 different CCZ gates for qubits. If the q is equal to 2, then you could either pick beta is 0 or 1. But if you picked beta equals 0, then this is just the identity. So we just have beta equals 1 and then suppress it. Here, there are many different CCZ gates to consider. So yeah, those are our qubits. And then we have this way of converting a qubit code with this nice transversal addressability for these sorts of gates down to a qubit code with the same sort of properties. And this goes via concatenation with a quantum multiplication friendly code, which were introduced in these 2 works from last year. These 2 works were considering transversal CCZs. Here we show that we can get a similar thing using for transversely addressable CCZs, but it's a simple argument. And so to be a bit more formal now, if we have a code for qubits, so for q-dimensional qubits, and it has parameters n0, k0, and d0, if q equals 2 to the s, we can convert this down to a qubit code with a transversely addressable qubit CCZ gate with the same number of logical qubits, with the same distance, and the number of physical qubits blows up by a factor of s cubed, there or thereabouts. And so our result one, the way it's obtained is you get an asymptotically good qubit code. So that's where K0 and D0 are scaling with N0. It's asymptotically good. And the qubit dimension is a constant. So if your Q is a constant, it also means your S is a constant. And so if K0 and D0 are scaling with N0, it doesn't matter that you throw a constant in here. This will still be asymptotically good. That's no problem. Result 2 is a bit different. Instead of using algebraic geometry codes, we use Reed-Solomon codes, which I'll go into them in a bit. They're just polynomials, nothing more than that. And these qubit codes are also asymptotically good. So K0 and D0 scale with N0. The difference here is that your qubit dimension Q is not a constant. It is scaling with the size of the code. Of course, then if Q is scaling with N0, then your S is something like log N0. And so when you get to here, you get polylog N0 times N0, K0, D0. That's why here our qubit code is only asymptotically good up to a polylog.
So the CCZ gate for the qubit here that you use, do you just pick one because like you have like this beta parameter, or like or it will work just for any of them, or?
Thank you for the question. Yeah, that's actually a great question. What we show is we get the qubit gate for any CCZ to the beta. And then once you've shown that, you can do the conversion, and you actually, I suppose you need the fact that you've got it for any CCZ to the beta, and then that will allow you to get the qubit CCZ. So yeah, the qubit code has all of them.
Okay.
And then
and I'm guessing like if you combine this oh yeah, I guess like it's a question then. So if you combine like this CCZ qubit gate with the qubit analog of Clifford gate sets, then would you need like all betas to get like the universal qubit gate set, or like just one of them, or?
Oh yeah, good question. So obviously, first obvious thing to say is if you take beta equals 0, so take beta equals 0 here, then this is going to give you just the identity. So that's not useful for anything. Okay, so now I'm going to say something which is like partially a guess, but I'm also fairly confident that for any non-zero beta, yeah, I'm pretty sure for any non-zero beta, this is non-Clifford, except I think, yeah, no, I'm pretty sure that's true. I was just wondering whether maybe the field itself has to be large enough, but I don't think it does. It doesn't. So yeah, I'm going to say with like 98% certainty that for any non-zero beta, this is going to be non-Clifford, and therefore is universal when combined with the Cliffords.
I see. All right, thanks.
Thank you. The only reason I'm not 100% certain is because it's nearly 11 p.m. And yeah, we're going to plow on. Cool. So yeah, algebraic geometry codes. The point is the qubit codes are always asymptotically good. But result 1, the qubit dimension's constant. Result 2, it's growing, which is why for result 2, you lose the polylog when you concatenate. So now we've reduced the problem. We want to get these codes for these 2 to the s dimensional qubits. How are we going to do that? Well, the key observation is that a diagonal gate like CCZ is going to commute straight through any Z stabilizer or any Z logical operator. And so it being transversal or transversely addressable is only going to rely on the structure of your X stabilizers and your X logical operators. This greatly simplifies the problem. We only need to worry about that side of things. Okay, there is this little caveat that we still want to be able to correct X errors. And so in that sense, we do still need to think about Z stabilizers. I'm going to ignore this issue. You'll just have to trust me, everything works out. The thing we really want to focus on here, because it's the novel thing, is the transversal addressability, for which the X stabilizers, X logical operators are the important thing. And once you've only focused on the X's, the problem kind of becomes quite classical because you're only thinking about one side of the issue. And what we do is we just write down whole X structure in a matrix. And by the way, there's a whole line of work going all the way back to Braby and Haar in 2012 of this kind of thing. What you do is you just write down this matrix. Bottom portion of the matrix, you say the rows of this are my X stabilizers, and then the top portion you say these are going to be my non-trivial X logical operators. And then the whole thing is just my group of X-type logical operators, aka everything that commutes with all my Z stabilizers. So if this looks slightly mysterious, let me say it another way. Normally, when you specify a CSS code, you would specify X-type stabilizers and Z-type stabilizers, and you would say, I need them to commute. Although another way to do it would be to say, let me specify the X-type stabilizers and the X-type logical operators. And then the everything that says X-type logical operators is the stuff that commutes with the Z-type stabilizers. So from this description, you could extract the Z-type stabilizers as all the Zs which are commuting with all of the rows of this matrix. So this is just another way to specify CSS code, but it's convenient for our purposes because it emphasizes the X stuff, which, as I've said, is all we really care about. What we're going to do, and as I say, there's a whole line of work doing this, is we're going to obtain one of these matrices as a generator matrix for a classical algebraic code. As a reminder, a generator matrix for a classical code is where you take a basis for that code and then you write down those code words as the rows of a matrix. So it's literally just a matrix whose rows is the basis for some code. In particular, its rows are code words. And so all our X-type logical operators will be code words of some classical code. It's the algebraic structure that is going to give us this transversal addressability. So let's look in depth now at the construction which gives us result 2. This is just based on polynomials, said in another way, Reed-Solomon codes, and so is slightly more transparent than the stuff which gives us result 1, which is the algebraic geometry codes. So first of all, let's recall what Reed-Solomon codes are. We start by taking some evaluation points, and this is n different points inside our field. And we will denote these points as eta1 up to eta n and refer to them collectively as just eta. We can then define the Reed-Solomon code over the evaluation points eta and of degree m. And this is a classical code, and every code word of this code is basically a polynomial. Okay, it's basically a polynomial, but a bit more formally, a given code word is you take a polynomial of degree less than m, you evaluate it at all these points, eta, and there's a code word. And then you take another polynomial, you evaluate it, there's another code word. And you form all your code words this way. And this is the Reed-Solomon code of degree m over the points eta. And Reed-Solomon codes are awesome. They are the codes given to us by God. There's no question. You know, they have great parameters. They do so many things super nicely. There's only one thing wrong with them, and that is that the field size Q has to grow with the field. You can see this automatically here. Like if you want n different points in the field Q, then or the field FQ, then of course Q is going to have to be at least n. So if you want n to grow and grow and grow, then clearly Q is going to have to grow as well. So that's the only issue with them. But even with that being said, oh, and by the way, this growing of the fields, you remember, this is what causes our QDIT size to grow, so we lose the polylog. What algebraic geometry codes do is they do this with Q constant, which solves that problem. Anyway, so let's have a look at our construction now. So our construction is as follows. Start by considering a subfield K of the larger field. And then we're going to pick some evaluation points. Start by picking some evaluation points, n of them inside the subfield. And then we pick K more evaluation points in some coset. So again, n in the subfields, k in a coset. And then given all of those evaluation points, we can consider a Reed-Solomon code over these evaluation points. So we consider the Reed-Solomon code of degree m over the evaluation points alpha union beta. And we're going to write down a generator matrix. Once again, generator matrix just means take a basis for this code, write down a matrix whose rows are that basis. And via row operations, I can write this in this form. And a lot of stuff's just appeared on screen. So what this is I'm taking the code over the points alpha union beta. The first thing I'm going to do is I'm going to just push all of the beta points to the left and all of the alpha points to the right. Then the next thing I'm going to do is I'm going to do row operations. The only non-trivial thing about this matrix is that the upper left k by k block is the identity and everything below it is zeros, okay? And then the rest of the matrix is just like whatever I get after doing these row operations. No, by the way, doing the row operations, that's equivalent to just changing the basis for the code. So you could also just say, pick a basis with like these nice properties and then write down the corresponding generator matrix. It would be equivalent. Notationally, we're going to write these rows as GA and the corresponding polynomials as G tilde A. And what's really important is that this code has k logical qubits. As written, this is kind of immediate in the sense that I'm defining my non-trivial X-type logical operators to be these k rows, and then the stabilizers to be these m minus k rows. And so as written, the fact this code has k logical qubits is kind of immediate because I have k non-trivial X-type logical operators. Although to prove this is legitimate, you have to do some more analysis. But anyway, as written, this has k logical qubits. And one more thing before I move on. This process of doing the row operations and putting it into this form with the identity up here and the zeros down here, and then we're only really considering this part and assigning X stuff to this part of the matrix. You might call that puncturing the generator matrix. But with that being said, and this is what we had on the previous slide, I'm now going to need two facts. Fact one is the fact that given any A labeling a logical qubit, so this is any A being one of these first k rows, there are some coefficients, gamma A1 up to gamma AN, in the field, such that given any polynomial of degree less than n, I can extract this polynomial's value at beta A by just taking this linear combination of its values at all the alpha i's. And this is nothing more than a polynomial interpolation statement. What this says is that if I have a polynomial of degree less than n, it is completely specified by its values at n points. And in particular, I can say exactly what it's going to be at some other point just by taking a linear combination of its values at those points. This isn't actually special to finite fields. This is just an algebra statement. So yeah, fact one is just polynomial interpolation. It's not deep. Fact two is so not deep, it's actually just notation. It's the fact that I have beta A and beta B were specifically chosen to be in the same coset of the subfield K. And that means that the difference between them, I call delta AB, must be in the field K. Okay, beta A and beta B in the same coset. So beta A minus beta B is going to be in the field K, and we call the difference delta AB, and it's in this field. And then the recipe that I mentioned earlier is this. If I want to address logical qubits A, B, C, and I want to do the logical CCZ operation on those three logical qubits, then the recipe is this. I do physical CCZ modulated by this gamma IA. So this was the power that I defined earlier. and then I'm doing it on these physical qubits. Notice that the physical qubits here are being labeled by these alphas, which is perfectly legitimate. These literally are our physical qubits. But then the key point is that alpha I plus delta AB is just some other point in the subfield, and therefore it is some other physical qubit because my delta ABs are in K. That's crucial. So this is a well-defined operation because these are other physical qubits. And then just for the sake of a question that was asked earlier was, can we transversally address any CCZ to the beta? And the answer is yes. And actually, it's quite simple from here. All you would do is you would say logical CCZ to the beta here, and then you would just put a beta in there. So just put a factor of beta in there before the gammas. And that's all. That would just do it for you. I definitely don't have time to give the proof of this, but I am going to talk briefly about how you upgrade this to algebraic geometry codes. This is just a reminder of things we've already talked about. The problem with Reed-Solomon codes, once again, the field grows, and so you lose a polylog when you concatenate. We would like a constant size field. And algebraic geometry codes are, there's no getting around the fact that they're more involved than Reed-Solomon codes. However, it's always useful to keep in mind that Reed-Solomon codes are or can be phrased as algebraic geometry codes, and there is an analogy of every notion in an algebraic geometry code in Reed-Solomon codes. And that is actually quite helpful to present the following. In our Reed-Solomon construction, we were considering polynomials. We were considering single variable polynomials over FQ. And then for the algebraic geometry, you're considering rational functions in M variables over FQ. Rational function just being a polynomial divided by a polynomial. I'm noticing now this M is actually slightly unfortunate notation because earlier I was saying take polynomials of degree less than M. This is different. This is just consider rational functions in a bunch of variables over FQ. And then for the Reed-Solomon construction, you're taking those polynomials and you're evaluating them at any old points in FQ. I mean, we were saying a little bit, let's take a subfield, but we're not too picky. It's crucial for algebraic geometry codes that we are evaluating our rational functions at specific points over FQ described by an algebraic curve. We've got this algebraic curve winding through this high dimensional space, and we evaluate our rational functions on that curve. It's a very beautiful idea. Polynomial interpolation, well, our version of that is just rational function interpolation. I've never seen this language be used before, but that's what it is, so we're going to go with it. And the really non-trivial thing is what to replace these shifts with. And this is why this result 1 wasn't in our earlier work. This is why it's still unpublished. It was not obvious what to replace these shifts with. But it turns out these shifts are, of course, they're affine functions. Affine functions are automorphisms of the Reed-Solomon code. And so what you want to do is you want to consider just more general automorphisms. You want to consider algebraic geometry codes with lots of automorphisms. And indeed, you can't just consider any old algebraic geometry code. This is why I said earlier, for our result 1, we have to take very particular codes. We have to take these codes. We need them to be transitive, and that means that our automorphisms can map anything to anything else, which gets us the full addressability. And we also need this iso self-orthogonality, but that really just means we can do rational function interpolation. That's really all that means. And such codes were constructed by one of the gods of algebraic geometry codes, namely Henning Stitzenhoff. And I can now summarize quickly. We've constructed the first quantum codes to support transversally addressable non-Clifford gates. We get them to be asymptotically good. Our results 1 and 2 had the complete addressability. They used very particular classical codes, but we also get more general constructions just with a lesser form of addressability. And we consider loads of different generalizations beyond qubits, beyond CCZ gates, and so on. there's a ton of interesting open problems, and we talked about LBPC-ness earlier. This is definitely the most exciting one. As I mentioned earlier, these properties show a kind of astonishing amount of logical control, but the code's not LDPC. And one of the reasons we don't have these for LDPC codes yet is because it is extremely hard to design LDPC codes with even transversal non-Clifford gates. There's so much work going on to get LDPC codes with non-Clifford transversal gates. I've listed 3 papers here, but there's so many of them, and there are none with transversally addressable non-Clifford gates. As I say, I think it's completely reasonable that the ideas in this work could apply to some of these constructions, but that's for the future. A slightly lesser challenge would be to optimize the constants. We can get asymptotically good codes, but it's interesting to ask what are the best constants you can get. And then finally, I just want to mention T-gates because it's close to my heart. T-gates behave weirdly differently to CCZ gates when you try to get them to be transversal, certainly transversally addressable, but even transversal. And there's still no asymptotically good or even nearly asymptotically good or even particularly good code with transversal T-gate, and certainly not transversally addressable. As I mentioned, we have this condition that says if you have this classical code with this property, then I can give you transversely addressable T-gates up to Cliffords, but we don't have any serious instantiation in mind. So T-gates is a very interesting thing to look into in the future. And with that, I'm going to thank you for your attention and welcome any questions.
Thanks, Adam. This was very pedagogical talk, and you covered many aspects. So people already asked questions, but let's say people like there 1 or 2 questions. If somebody has, maybe Andrew, if you have please ask. And
yeah, just a real quick one. So you mentioned like this conversion between qubit codes to qubit code, like where you have like that theta s cubed n something. So is that only for Reed-Solomon codes, or can you do that to just any code, any qubit code?
Oh yeah, you can do that to any QDIC code. Yeah. So we do actually have to do that in our algebraic geometry construction, because our algebraic geometry construction is initially built over like fixed qubits, yes, but they're not qubits. So it will be like, well, let's just think. So our smallest is, I think it's Q equals 256. I think. Yeah, no, it is. Yeah, so we still have to do this conversion to get down to qubits. It's just that you maintain the asymptotic goodness because the higher field is constant in size. So yeah, you can do that to any QDIC code with a transversal CCZ gate, with a transversally addressable CCZ gate. The concatenation with the quantum multiplication friendly codes is completely agnostic to the structure of the QDIC code. It's just saying if this has this logical behavior, then you expect the qubit code to have this logical behavior. What I'm now wondering is, because we've only really looked at this for like CCZ or CCZ type stuff, meaning stuff with plus and minus 1 entries. I'm wondering if the same holds for T-gates. I don't think it does, actually. I don't think the same does hold for T-gates. Yeah, I don't think it does. So, but yeah, the point is that you can do this for anything with a CCZ type gate.
Okay, and you have like this explicit construction to this conversion in your published paper, or is it in an unpublished work? Okay, all right, awesome.
Yes, and I do just want to properly credit the papers of Louis Golowich and Venkat Guruswamy from last year, as well as Quinn Young's paper, which introduced the quantum multiplication friendly codes. And they did that for the transversal CCZ gate we show that it works for transversally addressable CCZ gate, although it's certainly not like a big leap in any way. And yes, you can make these things fully explicit. Actually, just for the sake of mentioning it, you can do slightly better than this. What is my result? 2 gone. You can do slightly better than this if you use slightly better quantum multiplication friendly codes. You can up this to like n over 2 to the log star. So you can get something a tiny bit better than this by using quantum multiplication friendly codes that themselves have better parameters. So it turns out this can be improved slightly.
Right. Sounds good. Thanks.
Thank you.
Thanks for a very nice talk, Adam. I was wondering, so like here we're doing like depth 1 physical CCGs like all the time. Like, is there a nice way of thinking about the possibility where I do either depth 1 but like not the same physical operation on the qubits?
Sorry, just some understanding. Are you saying the possibility of doing a circuit that's depth 1, but it's like not the CCZ gate everywhere? It's like different gates?
Yeah. So allowing some freedom in the physical gates.
I mean, so one thing I'll say is that we are focusing mainly on diagonal gates with plus and minus 1 on the diagonal. And there's good reason for that. It basically comes down to the fact that if you're just dealing with plus and minus 1s, then essentially everything happens in binary. And all fields of size 2 to the s have characteristic 2. This is one reason why T gates are so much harder. And we can't apply these ideas to T gates. But to answer your question, our framework could handle very easily anything that's diagonal with plus and minus 1s on the diagonal. And in fact, our result 3, the physical circuit, isn't just CCZ. The physical circuit is actually Z, CZ, and CCZ. So yeah, diagonal stuff plus minus 1 on the diagonal. And basically, and you asked how can you think about that? How can you handle that? It's minus 1 to the power of a polynomial, where the polynomial is the effect of all of these gates. That's the nice.
That makes a lot of sense.
Awesome.
So are there any more questions? Yeah.
I was also wondering, so for example, we know that on the 3D toric code, like the CCZ there is not really depth 1, it's like depth 2, I think, based on the cup product.
Right.
Is there a way of fitting that into here as well?
Yeah, there's this kind of cheap thing you can do where you can basically just duplicate qubits. There's this kind of cheap thing you can do where if you have, like, say you have a depth 8 implementation of something, there's this kind of cheap thing where you can do where you just duplicate every qubit 8 times. And what that actually means precisely is concatenate your code with the repetition code of length 8 in the Z basis. So then, instead of hitting this qubit 8 times, you're spreading that qubit out 8 times and then hitting each one separately. And so in this sense, constant depth implementation and depth 1 implementation are the same thing, at least for theory. If you tell an experimentalist, just make it 8 times larger, they'll say, no, I'll just do a depth 8, what are you talking about? Anyway, and we actually have this in our construction. Like, if you actually read some of the more technical statements deeper into the paper, we're saying, this kind of thing, the QDIC codes here as we initially build them, the depth implementation is like 3 or 7 or something like this. But then we say, oh, you know, if that 3 and 7 are constants, we can duplicate qubits, so we can get down to the depth 1 implementation. And yeah.
Oh, I see. Oh, that's very nice. Thanks.
Yeah, no worries. Thanks for the question.
Okay, thanks a lot. Thanks, Jinming and Andrew, for the nice questions, and thanks, Adam, again for taking time to present it and answer everything with patience. So we will share the recording with you later. If you don't mind, can you share the slides so that we will share it with the people in the Discord, and I think I will stop the recording now. Okay. So